I will begin with a word of prayer. So, Heavenly Father, we thank you for the break and the time to relax and refresh and maybe spend time with family or something. And I just pray you help us to regain our focus, to complete the semester well, and just to best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. Okay, so today I'm going to try to talk to you about Euclidean domains and UFD. A UFD is a unique factorization domain, which is kind of what it sounds like. In a UFD, there is a unique way of factoring things into irreducibles, up to some pesky units to start. So that's where we're going. But there's still a bit of leftover business which we still need to attend to from our previous arc of the course. And so let's try to get this out of the way here, because I wanted to write it out and talk through it with you guys. So this is my theorem 3.5.21. So this technically doesn't quite fit under the title here, but it is a thing that we should cover carefully. So let F be a field. All right. And suppose P of x is a polynomial with coefficients in the field. All right. Then the ideal generated by P of x is maximal. All right. If and only if, I should say maximal in f of x, just to be clear there. If and only if what? P of x is irreducible over f. All right? So, hey, before I even prove this theorem, let's just take a second to smell the roses here, so to speak. What would be an application of this theorem? Probably the most famous one I could think of. How about this? If we look at f equal to the real numbers, certainly a field, right? And we look at P of x equals to x squared plus 1, right? This is certainly a polynomial over the reals, right? And you can prove that this polynomial is irreducible, right? Suppose it was reducible. What would that mean? It would have to be x minus r1 times x minus r2, right? In other words, if it had if it was reduced like this, non-trivially, then it would have zeros, right? The zeros would be, P of r1 would have to be 0, and P of r2 would have to be 0, right? But you can easily check that r squared plus 1 equals to 0 implies what? R squared equals to minus 1, right? But we know that every real number, there is no real number which satisfies this property, right? So that's a contradiction. No such R in R exists, which implies that, P of x cannot be factored. Which is to say, of course, that P of x is irreducible, right? So just to clarify, thus, P of x equals to x squared plus 1 is irreducible. And then what do we get? That says then that the ideal generated by x squared plus 1 is what? And what's that tell us? That says if we take the polynomials over the reals and quotient, by this ideal, we have a what? We have an integral domain, right? Because we proved polynomials over a field form an integral domain, right? Where, by the way, the only units in there are the constants. But anyway, integral domain mod a maximal ideal is a what? It's a field, right? And of course, you can tell me what that field is isomorphic to. No? Rational numbers, right? Wrong? What field is this? What does this thing look like? This looks like things of the form a plus b x bar, right? Such that what? X bar squared, well, excuse me, x squared plus 1 bar is equal to 0, right? What is that? This translates into x bar squared being equal to minus 1 bar, right? Which we typically would just write as minus 1 in this context as a slight abuse of notation, right? And so you can easily see that if you send psi of x bar equal to I, this will define an isomorphism from this quotient ring, factor ring, to the complex numbers. This is a way of constructing the complex numbers as polynomials mod an ideal. So this is part of the reason this is such an exciting theorem, is because it is very close to this example. If you can find irreducible polynomials, they give you maximal ideals. So when you quotient by them, you can construct fields. Okay? All right, so let's prove this theorem. You guys will help me, right? I hope. So which direction do you guys want to go first? Forward or backwards? What's that? Forward? Okay. I thought I heard of both. I was going to reject that. Let's see here. Forward. So we should assume that the ideal generated by P of x is maximal. What's that mean? What's that say? That says that if if I is an ideal, oh my goodness, this is really strong. You have no idea how strong this marker is. Goodness gracious. If I pass out, you know what it was. Oh my goodness. Oh. Great. Googly moogly. What can we say about I? Yeah, I is either P of x or I is the whole deal, right? This is what we mean by a maximal ideal. Okay. So that's what we got to work with. We're assuming that P of x is maximal. Now what are we trying to prove? We're trying to prove that P of x is irreducible. What's that mean? What's that mean? That means that if P of x is equal to, say, Q of x times R of x, then what? Right. Either the degree of Q is 0 or the degree of R is equal to 0. In other words, yes, one of them, I mean, in the context that we're currently working, those are the units. This is equivalent in our current context, aka either Q of x or R of x is in the units of this ring. Okay, so great. So what should we do? Suppose that P of x is equal to Q of x times R of x, right? Now, what can we say then?
The ideal generated by Q of x is going to be between the ideal generated by Q of x and
Like do a contradiction or over R. Suppose that the degree of one of those is positive, and then use it to construct it maybe larger than the one generated by P of x. I don't know if that would work, but that's just something.
Yeah. Let's see here.
So you're supposed to equal one of those with degree, but
Yeah, let's see here. What would this, I mean, this implies various things. This would imply that Q of x is an element of the ideal generated by what? R of x, right? Well, I'm sorry, I'm wandering, guys. I mean, that's true, but I'm not sure that's what I want. Whoa, one thing at a time. The ideal generated by P of x, you said. A subset of the ideal generated by what? Right. Let's just work with the Q for the moment. What's that say then? So Q of x is like, this is like my quote unquote I, right? That's the ideal that's between, possibly between P of x and the whole polynomial ring, right? So thus Q of x is either equal to what? It's either equal to P of x or what? The whole thing, right? I think there's enough data there, if we chase down the cases, that will give us a complete argument. We don't actually, I mean, it is true also that this is a subset of the ideal generated by R of x, but we don't probably need to use that if we just chase this, right? So let's see here. We're trying to prove what then?
If it's a unit, then that'll be fine. Because
let's see here. If it is a very dangerous word here. Q of x. If Q of x is a unit.
Because that'll show that it's irreducible.
Okay.
Well, Q of x is equal to the whole field of polynomials there, because then not I, 1 is in there, so that would immediately tell you it's a unit.
Very good. So in this, there's too many cases going on here. Let's call this case 1, right? And let's call this case 2 because I'm getting comments about both of them, I think, which is fine.
case 2 we handle first, case 1 we have to resort to.
Okay. So two first then. You say, okay, so then 1 is an element of this, right? Which means what? 1 is equal to Q of x times what? Times some polynomial, right? G, let's say. But by the degree formula, the degree of 1 is 0, and the degree of the product is the sum of the degrees, right? I mean, however you want to prove this, but here's one way to, if you don't believe me yet, you probably do though. I mean, do we really need to write this down? I don't know. Maybe not. The degree is non-negative, right? So if this is 0, it forces both of these to be 0 as well. Now, how else could you argue that? I bet you have a different idea, Sam. I mean, we're really just, in this case, in some sense, I'm reinventing the wheel. I'm proving that the only units in the polynomials are in fact, the constants, right? Because to have a product, 1 is equal to q of x times g of x, is to say that q is a unit, which we know is just the constants. Why do we know that? Well, it's this argument right here. Okay? So anyway, and again, getting back to your point, Zach, if q is a unit, we're done. That proves that that's not a actual reduction of p of x into genuine factors, right? So to speak. I mean, that's not a technical. So anyway, if q of x is unit, then p of x equal to q of x r of x is not a reduction. Okay, so step number, and going to case 1. So we're supposing, what is it? Q of x equal to p of x, right? Notice that p of x is equal to p of x times 1, right? So it's an element of this, right? Which is equal to that. Which is equal to the ideal generated by q of x. What does that say? That implies p of x is what? Q of x times what? Something. Pac-Man. There. But then what? See, or vice versa. There exists ghost. Q of x. I mean, if we can do it for p and q, we can do it for q and p, right? By the same line of logic. So then what?
So then we're given the degree of q. Oh, wait.
At some point, we need to use maximality again, right?
So we're given, oh, so the top thing gives that the degree of q is less than or equal to the degree of 3 p, and then the bottom thing gives the degree of p is less than or equal to the degree of q, therefore they must be equal.
Ah, very good.
And then given that, we get that the degree of r must be 0. So we're done.
But the only way you can thread that needle is to have them equal. The degree of p of x has to be equal to the degree of q of x, which says what? If the degree of p of x is equal to the degree of q of x, going back to our initial setup, that implies that r of x is what?
Degree 0.
Right. Which implies that p of x equal to q of x, r of x is not a reduction. I find this language to be helpful. I'm not sure how universal it is, but I don't know. I could say, therefore, p of x is not irreducible, but I don't know. I just like this language. It seems more direct to me. But that's because I generally think about doing things to equations as opposed to some other people. Okay, so that's the forward implication. How about the other way? So let's see here, the danger of knocking myself out. Suppose p of x is irreducible, right? Then p of x, let's see here. We want to show what then? we're trying to show that our goal is to show that the ideal generated by p of x is maximal, right? So let I be an ideal with what? P of x, subset of I, a subset of the whole thing, right? What's our goal? Our goal is to show that I is what? Either P of x or the whole set of polynomials over the field, right? Now, we know that f of x is a PID, right? What's that mean? Principal ideal domain. Every ideal is principal, right? Therefore, there exists g of x in fx such that what? Such that I is generated by g of x. So what's that mean? That means that p of x is an element of this thing, right? Because p of x is in here, and that's inside the ideal, which is to say that p of x is equal to g of x times r of x for some r, right? But p of x is irreducible, right? So what's that imply? Right? The irreducibility of p of x implies that either g of x or r of x is a unit. Now, if g of x is a unit, what do we got? If that's a unit, that implies that the ideal is equal to the whole thing, right? Because if the unit is in the principal ideal, then you can generate everything. One of the things we proved already. On the other hand, if r of x is a unit, what's that say? That says that the ideal generated by p of x is equal to the ideal generated by g of x, which is what we call I. So there you go. That's the maximality. Okay. I was going to make a side video to work through this, but I thought it would be healthier for us to go through it in class like this. So I did. There are, of course, still bits and pieces missing from my presentation in here. I mean, I am intending to cover up through section 5.2 in the text, right? Am I there yet? Yes and no. Right? Last time we talked about associates, irreducibles, and primes, right? And we talked about the relation between those in various contexts. We showed that there are contexts in which you can have something that's, well, which way does it go? You guys remind me. Which one implies the other, prime or irreducible? No, we did this already. So here I'll give you a lightning review of our last talk. We defined associates, irreducible, and prime. We saw that. Let's see if I found my thingy. Let's see if it works or not. Ooh. Ah, look at that. So looked at that example. I got confused. No surprise there. You guys unconfused me, though. Here's your homework exercise. Hooray. These examples are really kind of scary for you guys, but I do want you to understand them. Start with that. Integral domain. In an integral domain, every prime is irreducible. All right, so prime implies irreducible in where? an integral domain. And then what else do we get here? I just use this. If we have associates, they generate the same principal ideal. I just used that over here just a second ago. I had two things that were associates. I said that they generated the same ideal. I was using this theorem right there in this argument that we just looked at over there. In a principal ideal domain, what's a principal ideal domain? It is an integral domain in which every ideal is principal. Okay? So that's a little bit more than just integral domain. In a principal ideal domain, the primes and the irreducibles are interchangeable. And so you can tell from that then that this example that I looked at earlier here, we had an example, this 1 plus root minus 3 was irreducible, but it wasn't prime, right? Is that right? I'm trying to remember. Was that the point? One of these was irreducible, but not prime. But anyway, let me go on. Sorry, let me go on here. And then that's where we got to. So this is the next and final lecture that I'll cover for you guys from my notes from last year, all right? So here it is. So we need to talk about what is a Euclidean domain. And this is basically, a Euclidean, let me just tell you in colloquial language. A Euclidean domain is simply a set where you can do the division algorithm in an abstract sense. All right? So given two elements, you can construct a quotient and a remainder, just like we do for the integers. To do that, you need to have something called, now I call it a norm here, but most people would call this, probably should call that a valuation. Dr. Sprano calls it a valuation map. There's not a universal agreement on the language here, but there is universal agreement that a Euclidean domain is something that allows you to do the division algorithm. The question is, how do you set that up? If you look at the definition that's given in Nicholson, it's kind of close to this. And at some point, I'll write that down carefully for you guys. But anyway, long story short, there's some notion of distance. And if you take any two elements with b non-zero, you can find another element q such that a is equal to qb plus r, where this r is suitably small. In other words, the norm, or the valuation, the length, if you like, of r is less than the length of, or the norm, or the valuation of b. All right. Notice there's no assumption of multiplicativity here. So a multiplicative norm is like a stronger thing. If you have a multiplicative norm, you can prove that it's a valuation because this little argument right here, you can do the d of a is equal to d of ab divided by b. If that's dA times db, you can divide and multiply by db, if assuming it's non-zero. And so we get, since these are, since this is a, words, well, anyway, it's not, oh yeah, so if this is larger than or equal to 1, then clearly if I have like this over 2 or this over 3 or this over 4 or whatever, that's clearly larger, right? So, all right, I'm sorry, I'm majoring in the minors right now. Let me move on here. Examples are probably the better thing for us to look at. These are the three principal examples of Euclidean domains that we're interested in. You've already seen them. Number one, integers with absolute value defines evaluation. All right. Number two, the polynomials over a field with the degree function. The degree function forms a valuation, right? You notice that the degree function is not multiplicative, right? So this would not be a norm as I defined it previously, right? But it is a valuation. It does satisfy the inequality up there, and you can do a division algorithm for polynomials, right? In fact, some of you have been taught that in high school, right? Think about it. You were taught the long divide polynomials, right? That's the division algorithm, essentially. Fine, the division algorithm is a little bit more nuanced than that, but because the division algorithm, properly done, allows us to calculate the greatest common divisor of two things, right? That continues to be true over these more abstract rings. Gaussian integers. So you guys have proved that that's a multiplicative norm. Consequently, by the arguments I have right above, it forms evaluation, right? And I can actually kind of explain to you geometrically how to do this. Like how do you, this is a force of habit. Kang is in differential equations right now. I was asking him to turn the lights on in there, but I forget in here, it's up to me. But sorry, this is for just. By the way, as I get sicker this week, my lectures will get worse. So if you're understanding today, enjoy it while it lasts. You're like, get sicker. No, wait a minute, you monster. It's here. So in the Gaussian integers, right? You can look at this as, a lattice of points, right? Nah. Okay, I think I got enough points. And if I take two Gaussian integers, say a plus ib, and if I divide by c plus id, what do I have? I mean, if you think about this, this is a complex number, right? I mean, it's not a Gaussian integer anymore, but you still know what it is. It's not some kind of abstract, really, it's not really that abstract is my point. This is a concrete complex number you can calculate. In particular, this is a plus ib times c minus id over c squared plus d squared, right? So you can explicitly calculate ac, plus bd over, what? Shut up. C squared plus d squared. I don't know why I'm going into all this detail. It really doesn't matter. But I'm this far in, so I'm going to keep going. I'm not sure what you're supposed to learn from that, but there you go. It's either that I'm committed or I should be committed. But the point is this, right, is a rational. This is a complex number. It's somewhere in here. I don't know. It could be there, right? And if you look at that, it's got to fit somewhere in this lattice of integer points, right? And so there's got to be some one that's closest to that point, right? And that's what forms the Q. So you think of, the division algorithm. What are the letters I'm using? P, Q, R. Is it P is equal to QB plus R, right? So what's that say? That says Q is equal to what? Q is equal to P over B minus R over B, I suppose, right? Did I do that wrong? I probably did it wrong. Yeah, I think that's the point, right? In some sense, this is a excuse me, I usually look at it like this. P over B is equal to Q plus R over B, right? So you have an improper fraction. You're peeling off the piece, which is like a whole number, and then you've got the sort of proper fraction, right? I mean, this is a complex number I'm talking about, but same kind of idea. So thinking of this, I'll use a capital P and a lowercase b, capital B, like that. My point is this, goodness gracious. So this, P over B would be that nearest point, Q, right? Plus R over B. And my point is I can pick Q to be a Gaussian integer by simply just using the closest sort of Gaussian point, right? Let me be more specific. If this thing works out to like 3.2 plus 7.9i, what would you make Q? Yeah, 3 plus 8i would be a good choice. If you do that, what's left over is small enough that you can express it as a fraction where the size of R is less than the size of B. And I actually have an explicit example here. Here's a proof of what I'm trying to explain intuitively. You know, there's these points p plus 1, p plus 1 plus I, p plus I. This is a typical like point in the lattice of the Gaussian integers. If you take the quotient of two Gaussian integers, it's somewhere in there. And if you look at this s and t, they have to be what? They have to be less than, they could at most be a half, right? And if they're both a half, then the norm which you studied in problem 21 works out to what? I don't know. I think that norm is actually distance here, isn't it? Or is it distance squared? Distance squared. So I might actually be using distance in this argument. I forgot. But certainly the distance squared would be at most 1/2 squared plus 1/2 squared. The distance squared would be at most a half. Well, shut up already. All right. I'm talking to the computer, not you guys, of course. But anyway, the point is, being 1 over root 2, or the point is that I don't have words today. I'm sorry. It will satisfy the needed smallness for the remainder if you choose q in this way. Here's an actual example with some lack of calculation, but I was trying to show you the man behind the curtain, so to speak. Like here, I start out with trying to find basically the GCD of 11 plus 3i and 3i plus 2 over the Gaussian integers. So this is called the vector notation for the Euclidean algorithm. You write what you start with and then kind of keep track of what you do as you go. In so doing, you'll be able to see the linear combination of the initial elements in terms of everything you've done at the end without backtracking. So this extended Euclidean algorithm is what it's called in Stilwell. But yeah. Anyway, so start with this. Then, of course, the beta goes down here, right? And then I have 1 plus I, which is the remainder, formed by doing what? By taking 11 plus 3i and subtracting 2 minus 2i times beta. Now that's not obvious, but if you think through this idea, you can see how to come up with the q's actually by just doing calculator work. And so that becomes your new remainder, right? And then you divide by that. And to do that, I take my beta, I subtract off 3 plus I times, where was I? Anyway, it's a mess. But the usual Euclidean algorithm, it's not, well, I think you really have to do a homework problem on this to understand it. I hope I've assigned you one. Anyway, after I complete the algorithm here, I eventually get to the point of realizing that minus I is equal to 9 minus 4i times my beta minus 3 plus I times my alpha, where alpha and beta are the original two numbers I'm asking how are they related. So it turns out you can build a unit in the Gaussian integers as a linear combination of these two guys, which is to say that they're, in some sense, relatively prime. Right? Now, the thing is, depending on how you do the algorithm, this could either work out to I, it could work out to minus I, it could work out to 1, it could work out to minus 1. You can always take this and multiply by any other unit, right? You could make this equal to 1 if you like, but the Euclidean algorithm will not necessarily take you to 1. So anyway, these two numbers generate principal ideals, which are called comaximal because the sum of these two ideals is everything. So these two ideals are comaximal. In some sense, they're playing the role of relatively prime in this context. More on that later. There's a thought there I haven't completed yet. I'll come back to this page later. There is something we're building towards. So, all right. So the next so there's two very important definitions I'm sharing with you guys today, and this one, at least, I think I have the proper language for here. unique factorization domain. So let D be an integral domain. D is a unique factorization domain if every non-zero element of D can be written as a product of irreducible elements, all right? And in D, of course. And if the factorization of a given element of D into irreducibles is unique up to reordering and associates. In other words, if you can take x and D, non-zero, right? And x is equal to the product of x1 through xn, and x is also equal to the product of y1 through yn, right? Irreducibles. Then it follows that there exist units, u1 through un, such that you can associate the x's with the y's, right? And these are not ordered sets. Okay, I mean, they have to match up somehow. I'm not saying that 1 goes to 1 and 2 goes to 2. I'm saying 1 can go to n. Who knows exactly? But there's some reordering, right? You're familiar with this, right? Maybe from Math 200 even, we talk about primes and the prime factorization of integers, right? Like a lot of your sort of toy proofs are about that. So this is with us from the start of us talking about proofs, this idea of prime factorization of integers. I mean, that's the quintessential example of a unique factorization domain, is the integers. And the, the unique factorization of an integer and its prime factorization, which of course is good up to what? Reordering the primes. And also, what? You could, of course, I mean, we don't think about this much, but 25 is 5 times 5, but it's also minus 5 times minus 5, right? We don't think about that much, but technically those are also, if you want to get, those are associates. 5 and minus 5 are associates, right? We just ad hoc insist that the factorization be positive so that we don't always have to deal with positive and negative cases all over the place. It'd be annoying, right? Here we go. So the ascending chain condition in a PID, principal ideal domain, says the following. It says any strictly increasing chain of ideals, I1, I2, dot, 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 must be finite in length. This seems like a very bold claim, you know? I mean, that a PID, that's not a lot of structure, right? But here's how it goes. So you pick a chain of strictly increasing ideals, all right? Notice the strictly is important. If they were equal, that doesn't have to be finite. If they were equal, you could just fix to a constant and just stay there forever and ever. It wouldn't be finite, right? So strictly is important. Strictly increasing chain of ideals in a principal ideal domain D, you can look at the union of all of the ideals. That forms an ideal. If we take the union of ideals, we get an ideal. Remember, the ideal condition fixes the closure that fails for just mere subrings. Talked about that at some point. But it is true, the union of all ideals forms an ideal. These ideals, not all ideals in principle, but these particular chain of ideals, I'm thinking their union. So that I has to be generated by some D, since it's a principal ideal domain. But that means that D is in I, which means that D is in IN, right, for some n. What does that mean? But on the other hand, this is a subset of that, right? By construction, essentially. I mean, it's union. So that means that the ideal generated by about to go Looney Tunes on you guys. Let's hear. Again, this was what? Oh, this is for all I, isn't it? Yeah. Oh, for each I. I'm sorry, I can't read my own writing. But that's a subset of that, which means that I sub I is a subset of I sub n for each n, which means that what? That means that this I sub n has to be where? It has to be at the end of the chain because everything else is inside it, right? So that's where the chain has to terminate. If everything is in IN, then it must be that IN's the end of the road. Little set theory there, I think, but so IN must be the terminal ideal in the chain. and that's the ascending chain condition. I think this is due to Noether. Emmy Noether and her students brought modern algebra to what it is now. I mean, before her work, things were much different. A lot of the way we think is due to Noether. She died kind of early, unfortunately. She also had very, very deep ideas about physics, which we're still rediscovering. I think Noether's theorem was to every symmetry there corresponds a conservation law. This has been discovered by dozens of investigators who failed to appreciate the generality in which she proved it originally. So our next result here is the following. This is a big one. Every principal ideal domain is a unique factorization domain. All right. So here's the proof. The proof is beautiful, elegant, and really probably the neatest one I showed you this semester. And I don't think it's especially important that you write it down. I think if you read through it with me, it'll make sense to you. It's that clear, the argument. So here it is. We let D be a PID with a set of units U. We pick something in it non-zero, right? Our goal is to show that that has a unique factorization into a product of irreducibles, right, up to reordering. So there's 3 steps to the proof. Number 1 is to show that there is a factorization of A naught, which contains at least one irreducible. 2, show that there's a factorization into a product of irreducibles. And then 3, to show uniqueness up to associates. So point number 1, if we have A naught's irreducible, then we're done, right? So suppose it's the product of 2 things, right? Where A1 is not a unit and B1 is non-zero. Well, if A1 is irreducible, then its factorization contains an irreducible. So we're done, right? Otherwise, suppose that A1 is equal to A2 times B2, right? Where B2 is non-zero and A2 is not a unit, right? And so in other words, we just keep splitting it. We keep splitting it and splitting it and splitting it. If at any stage in the game we find an irreducible, well, great, we stop because we've shown that the factorization contains an irreducible. But otherwise, we continue. And so the rule is A sub n is equal to A sub n plus 1 times B sub n plus 1. We keep splitting it like this. But if you look at that, that means that the ideal generated by an is a subset of the ideal generated by an plus 1, strictly speaking. I mean, strictly so, because again, the Bn is not a unit, right? So we have a strictly increasing chain of ideals, which has to terminate. And it has to terminate at an irreducible. This is very sneaky. But there you go. So there exists an irreducible by this argument. And then if it is irreducible, well, suppose A naught is irreducible. We have a factoring into irreducibles. Great. Otherwise, we proceed much as we did in 1. We suppose that A naught is equal to P1 times C1. Again, if C1 is an irreducible, there exists an irreducible. So P1 we're assuming is irreducible, and C1 is a non-unit. So if C1 is irreducible, then we're done. We factored it into a product of 2 irreducibles. Otherwise, we apply 1 to C1 because it has to contain an irreducible in its factorization to get a C1 as P2 times C2. All right, and where C2 is not a unit. And so this generates another ascending chain of ideals. In particular, A naught is a subset of that, is a subset of that. It's strictly ascending chain of ideals. It has to terminate at finite length. And it has to terminate at, say, that. And by the construction of this chain, that forces this to be an irreducible. And so we get that any non-zero thing is a product of irreducibles. Product of irreducibles in our PID. Therefore, A naught is factored into a product of irreducibles. Now, the uniqueness. So if we have 2 factorizations, right, then we want to show that they're unique up to associates. So we're going to do induction on the number of things in the P's. If t equals 1, then we have A naught is equal to P1 is equal to that, right? To say that if s was equal to 1, that's the only thing possible. If we said s equals to 2, then we would have that this p1 is an irreducible is factored into two things which are not units. Oops, that contradicts the irreducibility. So we can't do that. So then by induction, we use strong induction here. Suppose that any factorization to less than t irreducibles is unique up to associates. This goes back to, remember we proved that the exercise I'm alluding to here is really just an extension of one of the theorems we've worked out in here already. I wrote it down. Theorem 3.6.10 on page 155 shows that prime, if and only if irreducible. So essentially what I need, this right here, if I've got P1 divides that, that means there has to be, P1 has to divide one of the Q's. That follows from the irreducibility of the Q's. And the fact that irreducible is interchangeable with prime, it's that idea. And then induction finishes it. This is very exciting because it means that, if you ask me about, can I factor polynomials over a field, the answer is yes. And can you do it uniquely, up to units, up to associates? The answer is yes. Yes, you can. This proves that. And it also proves, while we're at it, that there's a prime factorization of integers, because integers are a principal ideal domain. It proves both of those things in the same breath, using this dark magic of the ascending chain condition. That's, to me, it's a very beautiful genius that you see there. And so we have these beautiful corollaries. A field is a unique, polynomials are a field unique to a unique factorization domain. Every Euclidean domain is a principal. I should do this one next time. That one's important to go through the details of. But we'll see next time that we'll finish the story of connecting PIDs, UFDs, and Euclidean domains. So I shut up. Thanks, guys. Oh, I have your homework.